Hello everybody, today I want to speak about the climate reliability and resilience in the high voltage systems. Climate change is becoming one of the biggest challenges for the high voltage systems, as you know. Over the last 10 years, extreme heat, storms and wildfire have caused the major outages in these systems. Engineers now design HV assets with climate resilience as a priority. On the other hand, new materials monitoring and design approaches are helping to reduce the risk. In this talk, I will try to explore the advances, applications, and lessons learned in this field. Why climate resilience matters. HV lines and substations operate outdoors, fully exposed to the weather extremes. Climate-driven failures have led to blackouts affecting the millions of people. These recent disasters, like California wildfire and European storms, highlight vulnerabilities. Insurance and regulations now demand the higher reliability standards. Resilience has become as important as efficiency in the high voltage engineering. At first, I want to speak about the effects of heat and temperature stresses. High ambient temperatures reduce the cable ampacity and transformer life. In the last decade, the new high-temperature conductors have been introduced. On the other hand, advanced cooling systems extend transformer and converter stations lifetimes. Dynamics, Dynamic line rating allows the real-time adjustment of capacity during the heat waves. These measures, these measures improve the performance under the hotter climates. But the effect of wildfire and vegetation risks, I would like to tell you that wildfire linked to the HV transmission lines have grown as a global issue. On the other hand, utilities now deploy LIDAR and drone for vegetation monitoring. Insulator designs have improved to reduce the spark in the dry conditions. Automatic reclosing strategies are being modified to prevent fire ignition. Since 2017, wildfire resilience have been a key focus in the US and Australia. Another interesting issue is the effect of storms, floods, and salt sprays on the HV line systems. Coastal and island grids face the corrosion from the salt and humidity. Storm surges and floods threaten substations and underground cables. Over the last 10 years, utilities elevated substations and improved the drainage. Composite insulators and coating will reduce the salt contamination. These designs improve the reliability and coastal and tropical zones. In coastal and tropical zones. About the advances in the materials and designs, it is interesting to tell you that new composite materials resist corrosion and mechanical stress better. Nanofield insulation withstands the higher humidity and partial discharges, and this is very much important in the HV systems. Towers and foundations are designed to handle stronger winds. Switchgear housing now use the reinforced polymers for the durability. These advances make HV systems more climate-proof. About the monitoring and predictive tools, I would like to tell you that the condition monitoring has evolved into the climate-aware diagnostics. Weather data is integrated into the grid management for the risk forecasting. And most importantly, online sensors like temperature, vibration, and pollution levels um, is another important issue. AI models are able to predict the failure based on climate and asset health. These progresses will shift to the predictive resilience in a measure trends since 2015, and it is being continued. It is interesting to talk about some case studies or some interesting case studies. The California utilities designed HV protection after wildfire-related outages. Japan reinforced the coastal substations against typhoon-driven salt spray. Australia adopted bushfire-resilient insulators in the high-risk corridors. Europe upgraded storm-proofed towers after 2013 or 2014 winter storms. These examples show the adoption of, these examples show the adaptation of strategies in the practice. About the future directions, future HV systems will integrate the climate risk directly into the planning models. And of course, AI models are very much important. More undergrounding of HV lines is expected in fire-prone regions. Digital twins will simulate the climate impacts before building the assets. Research and R&D activities, in fact, into the self-healing and recyclable materials is accelerating, and this is a very good news. By 2035, the climate resilience will be built into all high voltage standards. In conclusion, I would like to tell you that in the last decade, the climate impacts have reshaped the HV engineering priorities. Heat, wildfires, storms, and salt stresses are the major design considerations. Advances in the materials monitoring and predictive analytics will improve the resilience. Real-world case studies show how adaptation is already underway. And finally, a climate resilient grid is key to a reliable and net zero future. Thank you.